3.5 is an overview of curve sketching. And we've done a lot of the pieces of this section already, and this section really just pulls in all the pieces that we've done from sections from 3.4 and 3.3, pulling those pieces into the idea of sketching curves, which you've been working on this, throughout your mathematics courses. You did some of this in algebra when you were talking about sketching like rational functions. You've done this before when you did high school algebra, when you talked about sketching parabolas. So this just pulls all those pieces in together in this one section. So the first thing we're going to talk about is some important graphical features. There are some pieces of information that as you're working through these that you need to find, or at least make note of, if not actually physically do any work to find them. The first one is the domain. In particular, domain means the x values you can have. But the reality is that it's often more helpful to look at that and say, what x values can I not have? And so some things like zeros and denominators, that kind of comes about here. Or negatives underneath radicals, things like that. The second one, vertical and horizontal asymptotes. Of course, these don't happen in all graphs, right? But they do in rational equations. So when we have denominators that are equal to 0, we get vertical asymptotes. And in the horizontal asymptotes, we had those 3 cases for horizontal asymptotes that we talked about back in chapter 1, I believe, where we looked at the degree of the numerator, degree of the denominator, and made some decisions. The third one says intercepts. Intercepts don't always have to occur either. Probably the classic example of a graph that has no x or y intercept is the graph 1 over x. 1 over x just has asymptotes along the x and the y-axis, so that doesn't have any asymptote or any x or y intercepts. But usually we do end up with some intercepts. So if x is equal to 0, that's actually the y-intercept. And if y is equal to 0, that's actually the x-intercept. So all of those pieces 1, 2, 3, that's all algebra stuff. You did that before you ever showed up in my classroom. You did it in multiple classes. But when you get into 4 and 5, that's actual calculus content. 4 and 5 are going to take a look at what we did in sections 3.3 and 3.4. Section 3.3 that you turned in today, that one was about first derivatives, right? And so we have lots of great information we can find out from first derivatives of a graph. If a graph is increasing, right, then it is equivalent to having a derivative that's positive. If a graph is decreasing, it's equivalent to have a derivative that's negative. And if you have a local min or max, then you will have a derivative at least that's 0 or doesn't exist. You potentially could have one that doesn't exist as well. In particular, though, what we look for when we're looking at derivatives is we tend to take the derivative, set it equal to 0, and then we follow through from there. We either create a line tape, like a line chart, to decide a number line to decide the intervals where things are happening, or what we found out in section 3.4 is that we could actually take those actual test points themselves and put them into a second derivative and test whether they're max or min. So those are the pieces of information that come from the first derivative. The second derivative is where we find out our information about concavity. So in particular, we look for where things are concave up, concave down, or where they have inflection points. And again, just like in the last chunk of material, if they're concave up or they're concave down, we find that information by first setting the second derivative equal to 0. So we set the second derivative equal to 0, and we do a number line, and we do test points, and we see, oh, when I plug this number back into the second derivative, do I get a positive or do I get a negative? And if I have a sign change, that is, which is a positive on one side and negative on the other side, then I have an inflection point. So these are the 5 pieces of information. I've organized them a little differently than your book did. I've grouped things a little bit more in the way we've thought through them. So if you look back at how the book breaks them down, it's just going to look different. It's all the same information, just in a different order. Now, in particular, once we get to the first example, you'll see that my directions look slightly different than the book as well because of that. On the directions, I just have the directions that say graph the function and completely discuss the graph. Okay, that's what it says. Your book says completely discuss the graph as in example 5.2 or something like that. You can use that reference as an example, that's fine. But you can also use what we're doing in class as sort of a list of 5 different steps that you're doing, and that's fine too. They're just in a different order. All right, so we're going to start with one that has pieces of it that you would have done before you got into this class. But because of the information you've now learned in this class, your graph is going to look different than it would have if you graphed this in college algebra, okay? Because you have so much more information at your fingertips than you did before. All right, so we're going to just go in order of the 5 different important information steps that I mentioned on the slides before. So the first thing is talking about domain. So what can you tell me, and you're going to need all the space that's at the bottom of this sheet of paper if you've got the notes printed out. So don't respect margins and things like that. Move all the way to the left and all the way to the right. You're going to need a lot of space because we've got a lot of details to fill in. All right, so we're going to start with domain. What can you tell me about the domain of this function? Okay, so the x values can't be 0. Anything else is good though, right? Okay, so the domain is that x cannot be 0. Or if you said it sort of in a positive way instead of a negative way, you'd say it's anything but 0. All right, what was the second thing that was on our list? Asymptotes. And in general, there are 2 types of asymptotes, or at least at most 2 asymptote types in a particular equation. And it doesn't always vertical and horizontal. It could be what? You could have a slant one as well. So while it's not actually listed over here in number 2, the slant asymptote is still a possibility. It's just not the more common of the ones we see, so I didn't put it on there as a list, but it is still an option. So in this function, we'll start with the vertical asymptotes. How do you find vertical asymptotes? Denominator equal to 0. So when we do our vertical asymptotes, we set the denominator, in this case x cubed, equal to 0. And so what does x equal? 0. So we're going to have x equals 0, which is a vertical line, which is the y-axis, as one of our asymptotes. How am I going to get horizontal asymptotes?
Look at the degree of the top and bottom.
Perfect. We're going to look at degrees. So what's the degree of the numerator? 1. What's the degree of the denominator? 3. So what will be my horizontal asymptote on this one? Y equals 0. This is one of those cases where the degree of the top is smaller than the degree on the bottom, then we get a horizontal asymptote of y equals 0. Everyone good so far? So we actually get both the x and the y-axis as asymptotes, one vertical, the other horizontal on this one. Third step is to do what? Our intercepts.
Didn't you say something about slant?
Say something else. What was
About
that?
the slant asymptote?
We could have a slant asymptote. When do we have a slant asymptote? Do you guys remember? Nope.
Let's see when the degrees are equal.
Close. When the degree on the top is bigger by exactly 1. So in this case, we don't have a slant asymptote. The degree on top is smaller. And also, if we have a horizontal asymptote, we don't have a slant asymptote. You get one or the other. You can't have both. You may have neither.
What is the way to find it? Slant asymptote.
How do we find the slant asymptotes? Do you guys remember? Long division. Oh, yeah, I heard that. You have to do the division of the numerator divided by the denominator. That's how you do slant asymptotes. Good questions. Yeah, we don't have to do it on this one, though, right? All right, moving on. Intercepts. Intercepts.
You never feel dumber than whenever you go to try to do a long division.
Actually, we get an intercept on this one, oddly enough. So let's kind of go through that. I understand why you're saying that, Mandy, and we'll talk about why it happens when it doesn't seem like it should. So Mandy said we shouldn't have intercepts because, and do you guys know why she said that or why we would think that maybe that's the case? Because those asymptotes. And those asymptotes do come into play, but we'll talk about a little bit more why. Let's actually go through the steps of trying to find them. We will be able to find one intercept. So one intercept is finding the y-intercept, that is where x equals 0. So what happens when we try to do this one? What happens if we try to plug in x equals 0? You get a 0 where? In the denominator. So this one that can't work. I mean, there is none. There are none, I guess, because you can't plug that 0 in the denominator. That's not okay. So we don't have any y-intercept. If we do an x-intercept, it means we let y equal 0. And in particular, if y equals 0, that says 0 equals x minus 4 over x cubed. You can think about it like this. That would be fine. And then you could multiply by the denominator, x cubed. Or you could recognize at this point, hey, if the whole thing equals 0, it means the numerator equals 0. Either sort of path you're thinking along, you end up getting that x minus 4 equals 0, So we actually get an x-intercept of 4. So this is at 4, 0. We do have an x-intercept. We do have 2 asymptotes. All right, so let's kind of chat about why, because that does seem odd, right? We've got these asymptotes. Why in the world, or how in the world, can we get an intercept if it's supposed to be an asymptote? I mean, asymptotes are supposed to be these things you don't touch. Well, the reality is that when you're dealing with horizontal asymptotes talk about end behavior of a graph. That is, on the ends of the graph gets very close to but does not touch them. They may actually cross them in the middle, and that's okay. Okay? So we are going to cross through at x equal 4 on this graph. That's a little bit different. What's next? There weren't just 4 steps, were there? 3 steps. 4. First derivative. All right. So we encountered something similar, an equation similar to this last time,
Oh, yeah.
or a couple times ago, and we said there's an easier way to find this.
Yeah. Because there's not.
Divide them into 2 fractions. Okay, so like this, Blaine? Since there's no addition or subtraction in that denominator, we can separate each piece in the numerator by the x cubed. Even if the denominator had plus or minus, we could do that. It's just that it wouldn't be helpful to do it. So because the denominator has a single term in it, it's helpful because I can actually reduce these and clean them up. So this is actually x to the negative 2 minus 4x to the negative 3. Right?
Yes.
Okay. Taking a derivative of that is easier because that's just power rules, right? No quotients, no products, no chains, none of that. All right, so let's take a derivative of x to the negative 2 minus 4x to the negative 3.
I'm confused on why the first one becomes x to the negative 2.
Because you have x over x cubed. You reduce it.
Divide out, then
You divide it up. Mm-hmm. The other thing you could think of it too, Jason, is if you brought that x cubed up, it would be x to the negative 3, and you could use powers of exponents. Positive 1 and negative 3 add to negative 2.
Okay.
Yeah. All right, so negative 2, what x, what's next? Oh, to the negative 3. And then what? Okay. Now what we're wanting to do, and I've had multiple people come to my office with questions about this particular point back in 3.3 or 3.4. If you're trying to set this thing equal to 0, that's good. I mean, that's what we want to do. But anytime you're dealing with negative exponents, we want to put the exponents back where they belong, so to speak, make them positive, because they're easier to work with. They're easier for us to think about, okay? So we're going to actually first rewrite this as negative 2 over x cubed plus 12 over x to the 4th. And if I want this set equal to 0, I have a couple of options. Now, in class, I don't know if it was last time or the time before, one of the options is we could separate them on either side of the equation, cross multiply. And that works. We can do that. Another option is we could get a common denominator, and we could combine the numerators. And that works too. I'm going to do the common denominator one this time because that's what I didn't do last time. So a common denominator here would be actually the x to the 4th, right? So we can multiply that first fraction, the negative 2 over x cubed, by x over x. And then the denominators will both be x to the 4th. And the numerators then are now negative 2x plus 12. So taking a look at this particular fraction at this point, I guess I don't need the equal sign over here anymore since we're not dealing with it from that perspective. But when is this function, this derivative, going to actually be equal to 0? At x equals 6, right? If you put a 6 into that numerator, negative 2 times 6, you're going to get negative 12 plus the positive 12 that's there. So this is going to actually happen. And if you want to see another step, basically what we're doing is we're setting the numerator equal to 0 and solving it. And if we do, we get x equal to 6 out of this. So we have a possibility of a maximum or a minimum at x equals 6. The other thing that we need to be aware of is if that denominator equals 0. Now in this case, when the denominator is equal to 0, we know we have an asymptote. But if this is equal to 0, that happens at x equals 0, it's going to be a part of our number line if we're doing the number line approach, right? So I'll go ahead and throw it in there for now because it doesn't always happen that it's an asymptote. So I don't want you to think that every time I see a denominator I'm going to get an asymptote. That doesn't actually always happen, but on this one it's going to. So we're going to put in that x equals 0 and the x equals 6 here. And we're going to test the points around them. So what values would you like to test? -1, 1, 7. Where do we test these numbers? Into the first derivative. So we're going to plug these into the first derivative. So f prime of -1, f prime of 1, and f prime of, 7. You can plug them into any version of the derivative that you'd like. The version of the derivative that's probably the cleanest is this one right here. But any of them will be okay. We could probably plug them into that one without it worrying too much. What happens to that denominator when you plug numbers in that denominator? Let me take a step back and ask a question differently. What are we looking for here when we're plugging these numbers in? If it's positive or negative. Okay, so we're really looking for the sign. What happens to the sign on the denominator? It's always positive because this is a power of 4, right? When you multiply something by itself 4 times, it cancels out any negatives you might have had. So we really can consider only the numerator and take care of our function on this particular one because the denominator is always positive. So I put -1 in the numerator, that is the -2x plus 12. Do I get a positive or negative? Positive. So this is a positive.
If you accidentally put in -12x plus 12 equals 0.
Oh, I sure did. Let me fix that. Thank you.
That freaked me out for a second.
Didn't mean to freak you out. I'm sorry. Let's fix that. How's that? Better. Thank you. Yeah, it should say -2x plus 12. Good catch. All right. How about we plug in the number 1? When I plug in the number 1, do I get a positive or a negative? I get another positive. And if I plug in the number 7, I get a negative. All right, so positive derivatives mean the graph is doing what? Hang on, slow down. Increasing first. So it's increasing in that interval, it's increasing in that interval, and then it's decreasing. So there is a location where I get something interesting happening here at 6. What do I have happening at 6? I have a max here. Now, in particular, I'm going to be graphing this point, which means in order to graph x equals 6, I need to know a y value that it equals, right? It's not good enough to say x equals 6 if I'm actually going to plot a point. So how can I find the y value that goes with x equals 6? The original equation. All right, so let's take a look back at that. Original equation that I was given. 6 minus 4 on top gives me 2. 6 cubed in the denominator gives me
36 times 6.
It is giving me 36 times 6. Do you know what it is? It's bigger.
216.
216 is right. So we have 2 over 216, which reduces to 1 over 108. Practically 0, right? Very, very small. That's less than a penny, because a penny would be 1 over 100. Okay, so this is 1 over 108. It is positive, but it's very, very close to 0. Good so far? Okay, we have one more piece of information we're going to find. What is it going to be? Second derivative. So let me do this on another slide, and we'll go back and forth between the slides for a little bit to try and get all of our pieces of information. Second derivative. You guys have your sheet in front of you. What will the second derivative be? So taking a look back over here at the first derivative, the one that's easiest to look at and find another derivative of is actually the one I'm boxing in red. That negative 2x to the negative 3 plus 12x to the negative 4. So let's take that very first derivative, there's the red, and let's use that to take our second derivative. Okay? So you guys tell me, what do I get? And we're going to do the same thing that we did next. Next, we're going to do the same thing we did on the last problem, which is what? Yes. So we're going to write this as 6 over x to the 4th minus 48 over x to the 5th. Then what? Common denominator is what I'm going to do on this one. Yeah, we could set them equal to each other because we're going to set it equal to 0. I'm going to use common denominator since I did on the last piece so that we're consistent in the particular problem we're working on. So I have 6x minus 48 over x to the 5th, and I'm going to set that equal to 0, right? what do second derivatives find us?
Concavity.
Concavity and inflection points. So if I set this equal to 0, I'm actually finding an inflection point, right? Okay. So that would actually mean that the numerator is equal to 0, which happens at what value? 8. Now, in my number line, I actually need to put in 0 and 8. Why? Yeah, because something might be happening different around the point x equals 0, because that's when the denominator equals 0, right? It's still a point of consideration. It still splits our graph into some pieces. And it does it because it's an asymptote on this particular graph. So I need to test some points, yeah? What points do y'all want to test?
-1
-1, 1, and 10. Okay, we'll test 10 this time. All right, so we're going to test them into what equation?
Second derivative.
Second derivative. So we want the second derivative at -1, the second derivative at 1, and the second derivative at apparently 10.
It just seems easier to work with.
Okay, what do we care about finding here? Okay, we're going to find concavity. We care about finding out where they're positive or negative, right? The sign is what we care about, right? So anytime we're doing test points, we care about signs. That's all we care about. So you don't even have to write the actual answer down. You just have to write the sign down. That's the important value. So if I plug -4 in, now, I'm sorry, -1 in, here is the equation I want to be thinking about. Let's pause for a moment and think about that denominator. That denominator is not like the denominator in the last part of the problem, right? No. It is x to the 5th, and x to the 5th is sometimes positive and sometimes negative. If I plug in -1, it's negative. And in the denominator. And what is it in the numerator? It's negative in the numerator. So if I have a negative on top and a negative on bottom, I get a positive. You guys are really animated today, man. What fun. It is positive. How if I plug in x equal 1?
As negative.
It's negative on top and it's positive on bottom, so the whole thing is... Maybe it's lack of sleep. Are we just a little punchy today? Okay. How about 10? Positive everywhere, right? Positive on top, positive on bottom, so this one's positive. Okay, so all this information tells us about concavity. So this is concave up, and then it's concave down, and then it's concave up. 8's an inflection point, right? And again, just like on the last one, I'm going to plot this point. So I need an ordered pair, 8 something. So I need to take that 8, I need to plug it back in to the original. All right, so the original one, 8 minus 4 would actually be 4. And then I need 8 cubed.
Oh, mercy.
256? Is that right?
No, 512.
512. Good try, Ben. All right, 512. So we have 4 over 512. Somebody reduce that for us.
1 over 128.
1 over 128. All right, so it is smaller than the other one, right? Because it's over a bigger denominator. But it's still positive. So we've got a positive value, but it's still very, very small.
Bless you.
Even less of a penny than the other one was. All right, so we're going to draw a graph with all of this information. We've got a lot of information to use.
Question.
Yes,
Why isn't 0 an inflection point?
because it's an asymptote.
Oh, yeah.
Yeah. It does change concavity there, right? It is going to change concavity there, but it's not going to be an inflection point. Inflection points actually have to be a point on the graph.
Okay.
All right, so I'm going to start with the, well, let's just go in order. What do we start with? The domain is x is not 0. So the second thing was asymptotes. So we'll start with asymptotes. We have asymptotes along the x and the y axis. Okay, is that good so far? How's your reading, bud? Excellent. Nobody's complaining. All right, the next one was intercepts. We had one intercept at x equal to 4. So I'm going to plot 4 here. And in fact, I know my graph needs to go out to 8 because I have values that went out to 8. So let me make my graph just a little bit longer over here. Okay, so I'm out to 9 right now. So here's 4. I've got something important happening at 6 and something important happening at 8. In particular, those values at 6 and at 8 are very, very small but positive. So I'm going to sort of stretch out my x and y axis just so that I can see, I'm sorry, my y axis anyway, just so I can see it a little bit more clearly. And these are going to be exaggerated because otherwise we won't even be able to see them. So the value is actually going to be here roughly, and then a little bit closer down here at x equal to 8. So those are the 3 points that I know something about, right? One is slightly more positive than the other one. I think I've plotted everything except for the increasing, decreasing information. Does that look pretty close to you? Is there anything else I've missed so far? Okay. Let's start on the far left of the graph. The far left of the graph, that is the values that are less than 0. Look at these number lines that we have created. The first number line over here about increasing, decreasing says that the graph is supposed to be increasing when we're less than 0, right? And the second piece of information says it is supposed to be concave up. So how is the graph going to be increasing and concave up? Okay, so you guys are drawing concave up beautifully in the air, but you're not drawing completely increasing. Did you catch yourself? You almost drew parabolas for me, didn't you?
Because this half of the view.
Yeah, it will look like an exponential curve. So it looks something like this, right? That's increasing, and it is concave up. The only other option, mind you, would have been to do this. I mean, it has to be in one of those two places. And what's this doing? It's concave down, and it's decreasing. So that's not the one we want. Okay, so here's the one we want. Increasing, concave up. All right, next piece of information, let's go from 0 to 4. So if we go between 0 and, actually 0 and 6 is actually a lot of all the information on this particular one. What is supposed to be happening between 0 and 6? Careful.
Increasing.
It is increasing and concave down. So what's that going to look like between 0 and 6? Yeah, it's going to be below the x-axis, and then it's going to come above. And we do know 6 is the maximum. That's exactly right. So this piece looks something like this. All right, now between 6 and 8 is different, because if you take a look over here, the derivative from 6 on is actually negative. So we've actually going to have a decreasing graph from here on out, right? Graph has got to be going downhill from 6 on. But until we get to 8, the graph is still concave down. After 8, we've got to be concave up. So this graph looks something like this, because that's concave down. And then it needs to be looking like it's curved back upward to be concave up. You didn't know all of that in your college algebra classes, right? Or algebra in high school. You didn't have the ability to think about this maximum minimum feature or the concavity features. The best you would have had at that point in time would have been to plot some points and to try to connect them in a way that was reasonable. So you have more tools at your disposal now. Take your calculator real quick, graph it. Make sure that it looks reasonable. Please do that. And when you get to your test, if you don't do that, you're not going to get a lot of sympathy from me, because you have that calculator for a purpose, right? And what we're using it for at the moment is to be able to check that what we've done is reasonable. Okay, just a standard negative 10 to 10 graph should work for you. You can hit 0 to 6. That's one way to do it quickly, too. What do you think?
It doesn't have the end of it on there. But
You can't see the end of it because it's too close to the x-axis. That's why. Everything else look good? Excellent. We're going to do another one that's easier. How's that sound? Okay. The calculus part of it, maybe that part's not particularly easier, but the graphing part of it's much easier. So, this graph is the graph of a radical, right? Got a square root going on here. All right, so we're starting with number 1, the domain. Can you tell me about domain for this guy?
it has to be greater. Oh, just kidding.
Can equal 1/2.
Yeah.
Well, actually,
It has to-
Okay, keep
all
thinking.
the numbers, right?
Is it?
Except
As
for
long
where
as
you can get lower than
2.
0.
Okay, so you can't get something to be less than 0. What can't be less than 0?
The value under the right.
the value under the radical. So whatever is under the radical, in this case, that's 2x minus 1. All of that has to be
X is less than 1/2.
greater than or equal to 0. So no negatives underneath the radical. So for it to be not negative means it's positive or 0. Everybody good with that part? Okay, so we're going to solve this, which is what you guys keep doing in your heads. This says x is greater than or equal to 1/2. Right? So my graph will not have any values before 1/2. Which means I definitely don't have a y-intercept, do I? No, I don't. Okay, so the next thing says asymptotes. What can you tell me about those? What? There aren't any. There aren't any. This isn't a rational function. So I don't have any denominators. If I had a denominator, we could talk about vertical asymptotes. And then we would look at whether or not maybe we had horizontal ones. We don't even have a denominator. So there aren't any asymptotes on this. There's none. Now, intercepts, we know that we do not have a y-intercept, right? Because I can't let x equal to 0, because if x is equal to 0, then I would have a negative underneath the radical, right? So there aren't any of these either. How about an x-intercept? That is, what happens if I let y equal 0? This is at x equal 1/2. That is going to be the smallest value that I can get on my graph. So I do have an ordered pair that is the x-intercept at 1/2, 0. Okay, everybody good so far? When things don't exist, they go faster, don't they?
Yeah.
They do. All right, the second thing we have to do then is to look at those increasing and decreasing pieces. That's the calculus piece that's really going on here. So number 4 is to look where the graph does what? What am I looking for? Increasing, decreasing, and how do I find it? First derivative. And on this one, my first derivative actually is going to involve what? It is going to involve the chain rule calculus. That's true. It will involve calculus. Thank you. Must be April Fool's Day, right? 2x minus 1 to the 1/2. It does involve calculus. Yes, it does. All right, somebody tell me what the derivative of that is. You guys are getting good at derivatives now.
1/2 2x minus 1 to the negative 1/2.
Times 2.
Excellent.
We have awesome teamwork skills.
You guys do have awesome teamwork skills. All right, so what do you see can simplify here?
2 1/2.
The 1/2 and the 2. So this can actually be written as 1 over the square root of 2x minus 1, right? What in the world am I looking for or doing with this piece of information?
No idea.
Equal to 0.
Usually you're setting it equal to 0 or to doesn't exist, right? There's a different thing that we haven't encountered this happen. This is the first time we've encountered this happening so far. What can you tell me about let's do the doesn't exist part yet. Where does it not exist? At 1/2, right? And actually anything less than 1/2, because I can't plug in anything less than 1/2 either because that's square root. But in some sense, we kind of already knew that was the issues with the domain that we already dealt with, right? What about the x equals 0 part here? I'm sorry, the function equal to 0 part here. It will never equal 0. Why?
Because there's no variable in the denominator.
There's no variable in the numerator, right? That numerator is a plain old simple 1, and 1's not 0, and it can't ever be 0. So, yeah, we don't have any maximum or minimum point here because the derivative never equals 0. What that means is that the graph is either always increasing or always decreasing, because otherwise, if it changed, it would have a max or a min. So we need to decide, is it always increasing or is it always decreasing? So why are you saying it's always increasing, Taylor?
Because it's positive.
Okay, so the one on top is positive. Tell me about what you're thinking on the bottom.
It can't be. I guess it can. Well, no.
You can't have a negative underneath the radical.
Okay, but even if you
It can be
could,
plus or minus, can it? Even if you take it.
if you had a plus or minus in there already. Okay, so what we're dealing with is this idea of square roots, okay? That denominator is a square root of something. Agreed?
Yes.
When you take a square root in a problem that's already given you the square root notation, they're asking you for something called a principal square root,
So maybe it has to be positive.
which assumes it has to be positive.
Okay.
So when a square root is already given in the problem, it's asking you for the positive part of that, always. The only time that you get the plus or the minus is if you put the plus or the minus on because you put the square root in there. You guys remember that from somewhere in completing the squares, probably where you first talked about it or something like that. Since you put the square root in, you had to put the plus or the minus. Well, if the square root's already there, it's always positive. That denominator is always positive. Now let's take for a moment and just consider the fact that if you didn't want to think about it that way, there's one other way to think about it, okay? You can pick an x value. Any x value bigger than 1/2 because our domain's only x values bigger than 1/2, okay? What's a really nice value bigger than 1/2? 1. 1. Not 7. 1. Oh, goodness. All right, so if we put in the number 1 into that derivative right there, what happens? Well, you get a positive on top. What do you get on bottom?
Positive.
A positive. So you can actually just test a point, right? Into this derivative. This is positive, and we've already talked about the fact that whatever it is, it's this everywhere, because otherwise we'd have a max or a min, and we don't have one. So this thing, it cannot equal to 0, which means there's no max or min. This positive tells us it's increasing and in this case it's on the interval that we have, which is 1/2 to infinity. So it's increasing everywhere on the domain, increasing on the domain. All right, one more piece of information. What do I need? Second derivative. So then, my second derivative is most easily found using the derivative right here. Oops, let's try it in green so I can get a different color. All right, the part that's circled in green, because I canceled out the 2 and the 1/2, I can use that to find my second derivative. What will my second derivative be?
They had 3 halves. Times 2.
Right. Is everybody good with that? What simplifies?
1/2.
All right, this 2 and this 2, or that 1/2 and that 2. This one still has a negative out there in front, though, so we don't want to lose that. I've got here on -1 over, I'll just write it as 2x minus 1 to the third, and then square rooted. Or you can write it to the power 3/2. It doesn't really affect anything either way.
So if you were, okay, so I realized that like in the first derivative, the 1/2 and the 2 canceled.
Mhm.
If you were to go back through and still write that in there, would you still get the same answer?
You would, but you're going to have to cancel it then again to get your simplification, yeah.
Okay.
Eventually you're going to reduce it again the second time, so you might as well use the reduced one when you're working with it. All right, this also cannot equal 0, right? Yeah. I mean, this does not have the ability to equal 0 for the exact same reasoning that it couldn't before. And again, we can talk about plugging in a particular number if you'd like, or we can talk about it in general and recognize on top we've got a negative, on bottom we've got a positive. So this graph is always negative, which means it's concave down, right? Negative second derivative. So f double prime of x is negative, which means it's concave down on the interval 1/2 0. I'm sorry, 1/2 infinity. So this graph is always concave down and it's always increasing. And we have one x-intercept. That's the only information we have to plot. So, are you ready to plot it? Yes, thank you. All right, so here is our graph. And the x equals 1/2 is somewhere like right here. And I can plot my point there. I need to draw a graph that is increasing and concave down. So what will that look like? Most of you are showing me something that looks inside.
Can you go back to the last slide just real quick?
Mm-hmm. So we've got it's increasing, so it's above the x-axis, right? And going further above, but it is concave down. It is getting less steep as we move along, right? Any questions on that one?
Wait, so how does that make it concave down?
Concave down is a description of how the slope of this is changing. The slope here is actually becoming less positive. It's less steep as you move from left to right. It's very, very steep on the left, and it's less steep on the right. We kind of have this feeling of it sort of being a cupping feature, like it's cupping down or opening downward in that way. Any questions on that one? All right.